Hello friends. So today we are going to solve total of 7 questions. 1997, 2 questions, 98, 4 questions, and from 99 we have 1 question. And the topic is our heat and thermodynamics. So the first question, it states that a ring-shaped tube contains two ideal gases with equal masses and relative molar masses M1 32 and M2 28. The gases are separated by one fixed partition and other movable stopper S, which can move freely without friction inside the ring. The angle alpha as shown in the figure is. So basic diagram is given to us, and this is our M1 and M2, and let us suppose our M1 is the representation of our gas 1 and M2 is the representation of our gas 2. Okay, their respective molar masses are given, and so we have a fixed position and other one is represented as S, which is a movable position. Okay, so at particular instant the stopper is at this particular position such that the angle between the two is given as alpha, which we are supposed to find out. Okay, so let us start with the, you can say that we have a gas 1 and its molar mass is given as M1, which is 32, and it is also mentioned that they are of equal masses, both the gases. Therefore we can write that their actual mass, or simple we can write it as a mass. Suppose that is small m1, which is equal to per m. Okay, and then we are having our gas 2, whose molar mass that is M2 is 28 and its actual mass is, let us suppose, M2, and which will obviously equal to mass of the gas 1, which is M. Okay. And it is said that they are, because the stopper is going to take one fixed position such that the pressure will be equilibrium and there is no friction, and also we can say that it will be also in the thermal equilibrium. Okay, so we can say that equilibrium condition and for gas 1, let us suppose pressure is P1, and for gas 2, let us suppose the pressure is P2. Therefore we can write the equilibrium condition pressure for gas 1 will be equal to pressure for gas 2, or we can write our P1 is equal to P2, and with respect to, we can say, our temperature, we can assume that it should be in thermal equilibrium. So we can say gases are in thermal equilibrium and let us suppose the temperature is T1 and its temperature is T2. Therefore, we can write that our T1 is equal to T2 is equal to our T. And we can also find out that if the ring is having a area A, or we can say area of cross section of the ring cross section for ring, let us suppose that is given as A. Therefore, we can write that the total volume of the ring, so from here we can write that total volume of the ring, let us call this as V total, will be equal to 2 pi r multiplied by A. Okay. And 2 pi r is nothing but our circumference of the ring. And this is a general formula. We can say modify it according to our internal as well as the external also. So not a big issue. Okay. So now we can find out the volume because of gas 1 and volume because of our gas 2. So we can say that volume of gas 1, which is our V1, and V1 will be equal to our alpha upon 360 multiplied by 2 pi A. Okay. And 2 pi RA. Okay. And we can write this will be equal to alpha upon 180 multiplied by pi R A. And volume for gas 2, that is our V2, will be equal to our 360 minus alpha divided by 360 multiplied by 2 pi r times A, which will be giving us 360 minus alpha divided by 180, and this comes as a pi r A. Now we can use the equilibrium condition but with respect to our ideal gas equation. So we can say our ideal gas equation, which gives us that PV is equal to nRT, and here N is our number of moles, which is equal to our actual mass divided by its molar mass. Okay. And we can divide this, we can say for gas 1, number of moles is our N1, its actual mass is our M, and molar mass is our M1. So we get this as M upon 32. Similarly, we can write this as our N2, and let me write this as M1. So this will be our M2 upon capital M2. This will be coming as M upon 28. And we can write the equation for the pressure. So we can say our P1 will be equal to N1R T1 divided by V1, which gives us this will be over MRT divided by 32 times V1. Similarly, we can write our P2 will be equal to N2RT divided by V2, which gives us MRT divided by 28 times V2. At equilibrium, like we said, P1 should be equal to P2. So we can say at equilibrium, P1 is equal to P2. So we get this as our MRT. This should be actually T1 and this will be our T2. Okay, later on this is our T2 and T1 is equal to T2 is equal to T. And we get this as MR. This will be our 32 V1 is equal to MRT and this is about 28 times V2. And MRT goes away. So from here we can write that our V1 will be equal to 28 by 32 times V2, or simply we can further solve it. This will be coming as 7 by 8 times V2. Okay. Now we already know their respective V1 and V2 in terms of angle. We already know, so we have our V1 as well as V2, so we find out their ratio. Okay. So let me write it in the ratio form, much more easy to substitute later on. And we can say that our V1 upon V2 in terms of our angle alpha will be equal to our alpha upon 360 and multiply by 2 pi r times A, and this will be 360 minus alpha upon 360, and this comes as our 2 pi r upon A. And here 360 2 pi r cancels out, and this comes as alpha upon 360 minus alpha, and this will be equal to our 7 by 8. Now it is quite easy to solve. Now we can write this as 8 alpha is equal to, this will be coming as 7 multiplied by 360. So this will be over 0, this will be 2, and this will be 25 minus 7 alpha, which gives us that our 15 alpha is equal to 2520, and giving us that alpha is equal to 168. Okay. No, sorry, one thing I calculated this angle basically. Okay, but we are required to find out this particular angle. So for the time being, let us consider we calculate this as alpha, and we need to find out this alpha prime. Okay, for the sake of convenience, I think it should be actually, this should be our alpha and this should be 360 minus, but anyways it doesn't matter. We are going to simply substitute. So I can say we are required to find out this alpha prime, and this angle is of alpha prime. So I just found out alpha, so I'm going to subtract it by 360. Okay, I think I missed it. Therefore we can say that our alpha prime will be equal to 360 minus 168, giving us 192 degrees. Okay, now it's the correct one. Okay, there is no change in the solution. Okay, so this will be our 192. Next question. It was asked in the year 1997, and it states that a gas thermometer is used as a standard thermometer for measurement of temperature. When the gas container of the thermometer is immersed in water at its triple point 273.16 Kelvin, the pressure in the gas thermometer reads 3 into 10 to the power 4 Newton per meter square. When the gas container of the same thermometer is immersed in another system, the gas pressure reads 3.5 into 10 to the power 4. The temperature of this system is therefore. So basically it is, you can say, directly based on the you can say gas thermometer principle, that our pressure is directly proportional to our temperature. Here volume will be our constant. Okay, so that's the only thing here. Okay, so we can say our gas thermometer principle and for volume as constant, we can write that our pressure is directly proportional to temperature. And we have two states, so we can divide this as, or we can write this as P upon T is equal to constant, or we can say that our P1 T1 is equal to P2 T2, and we are supposed to find out our T2. Okay, so we can say that our T2 will be equal to, we have this as P2 upon P1 multiplied by T1. We simply substitute the value. This comes as our 3.5 into 10 to the power 4, 3 into 10 to the power 5 multiplied by 273.16, which gives us that T2 is approximately equal to 318.69 Kelvin. So this was quite simple. Next question. It was asked in the year 1998, and it states that 1 mole of ideal monoatomic gas is taken around the cyclic process ABCA as shown in the figure. Calculate. So based on this, we are having 4 questions and basic figure is given to us. So it starts from A, moves with the constant volume to B, then it moves from our, you can say, BC, which is basically a linear relationship, and then at constant pressure it comes back to our A. So we can say our AB is our isochoric process. So we can say our AB is our isochoric, and our BC is our linear PV relationship, pressure volume relationship, and we have then our CA. CA is having constant pressure, so it is our isobaric. So First of all, let's find out part A, that is work done by the gas. Work done by the gas. So basically this is a cyclic process, so we can directly use the formula that the work done by the gas is the area enclosed by the cycle in a PV diagram. Okay, so we can say that our work done by the gas is equal to area enclosed by PV diagram. And this is our, you can say, right angle triangle. Therefore we can write our base that is from C to A, okay, and this will be our 2 V0 minus V0 giving us our V0. And then we come to our height, and height is our A to B, and this comes as our 3 P0 minus P0 giving us twice P0. So work done, and let us suppose that work done is represented as W. Therefore we can say that our W is equal to right at angle half base into height, which comes as our half V0 twice P0. This 2 and 2 goes away, and we get this as our P0 V0. So this is the work done by the gas. And the heat rejected by the gas in the path CA and absorbed by the gas in the path AB. Okay. So we come to our part B. So we come from path CA. Okay, so our path CA is our isobaric, and isobaric, our pressure is given as our P0, and our volume, it changes from 2 V0 to V0. So here we can use our first law of thermodynamics. So we can say that first law of thermodynamics, it gives us heat for path CA will be equal to change internally for path CA plus work done for the path CA. And first of all, let's find out the internal energy. So we can say our change in internal energy is our basic formula is our NC of V, and we have this as delta T, and the gas given to us is our monoatomic. Therefore we can write that our C of V is equal to 3 by 2 times R, moles is given as to 1. And we are supposed to find out delta T. So for that we can use our ideal gas equation. So we can say our ideal gas equation, which gives us that a PV is equal to nRT. So for 2 points, one is our C. For C we can write this as a PC, and VC, number of moles is 1, and this is R, and we can write this as our TC. Okay. Therefore we can say our TC, PC is our P naught, and VC is our twice V naught, and divided by R. So this comes as our 2 P naught V naught divided by R. Similarly, we write for our point A. So we can say our PA VA is equal to 1 R TA, giving us TA will be equal to PA is our P naught, and VA is our V naught, and this comes divided by R. Now we can find out our delta T. Delta T will be equal to TA minus TC, which gives us a P naught V naught upon R minus 2 P naught V naught upon R. This gives us minus of P naught V naught upon R. Therefore we can write that our delta change internally for CA is number of moles 1, 3 by 2 times R, and this comes as minus P naught V naught upon R. R and R goes away, and we are left with this as minus 3 by 2 P naught V naught. Now we can find out our work done we required, because we found out our change in internal energy and we find out the work done now. And we can say work done on the gas that is our WCA will be equal to pressure change in the volume. Pressure is our P naught, change in volume comes as V naught minus twice V naught. So from here we get that our WCA will be equal to minus P naught V naught, and therefore energy QCA will be equal to our, this comes as minus 3 by 2 P naught V naught minus P naught V naught, it comes as minus 5 by 2 P naught V naught. Okay. So it means the heat rejected is our 5 by 2 P naught V naught. Okay. And part B, heat absorbed by the path AB. Okay. Same process we can use, and path AB, okay, path AB is our isochoric. You can say path AB, which is our isochoric. And same equation, QAB will be equal to, because it is at constant volume, so work done will be equal to 0. So therefore we can write this as directly as N C of V and delta of T. We can easily find out delta of T. For point A, TA will be equal to our P naught V naught upon R, and our TB will be equal to our 3 P naught V naught upon R. Therefore, delta T will be equal to TB minus TA. So we get this as our 3 P naught V naught upon R minus P naught V naught upon R, which comes as our 2 P naught V naught upon R. Therefore, QAB N will be equal to 1, and so this comes as 1 3 by 2 times R, and this comes as our twice P naught V naught upon R. Here R and R cancels out, 2 and 2 goes away, so we are left with only 3 P naught V naught. So it is a heat absorbed. Okay. And we come to part C, the net heat absorbed by the gas in the path BC. Okay. So we come to the part C, and from B to C there is a linear relationship. Our process is our PV linear relationship. Okay. So it is asking from B to C, and that is a linear pressure volume relation. And we can use our first law of thermodynamics, which gives that Q of BC will be equal to delta U of BC plus work done because of the BC. So let's find out our work done. And for our work done, we have to find out the equation of the line. Okay. So we can say our work done, which is our WBC. So we can write that our equation of line for this BC can be written as P is equal to mV plus C. Here m is the slope, which we can calculate easily. We can say our m is equal to P naught minus 3 P naught, and this is about twice V naught minus V naught, which comes as minus 2 P naught V naught. And if we use with respect to point B, so we are going to use our point B, whose coordinate is our V naught thrice P naught. Therefore, we can write the equation that will be coming as our thrice P naught is equal to minus of twice P naught V naught times V naught plus C. And here V naught and V naught cancels out. So from here we get our C is equal to 5 times P naught. Therefore, the final equation, we substitute value of M as well as C, we get that our P is equal to, this is minus 2 P naught V naught plus 5 times P naught. And work done, which we are supposed to find out, will be equal to integration of our initial volume, that is our V naught, final is our twice V naught, and we have this as P dV. We substitute value of you can say the equation for our P. We get this as WBC will be equal to integration V naught to twice V naught. This means minus 2 P naught upon V naught plus 5 times P naught multiplied by dV. And this can be written as, this will be coming as minus 2 V naught, and it will be our V naught square, and this will be our twice and plus 5 P naught V naught. Limits goes from V naught to twice V naught. And oh sorry, I missed, this is our missed here, this is our V also. Okay, so here it is our V and here it is our V square, and similarly here it will be also V. So this twice and twice cancels out, and we get this as minus P naught, and this will be upper limit is our twice, so this comes as our 4 times V naught square divided by V naught plus 5, and this become 10 P naught V naught minus lower limit is our V naught, so this comes as minus P naught V naught square plus 5 P naught V naught, and this square goes away here also and here also. So we are left with here as minus P naught 4 P naught V naught, and this is about 10, so this will be coming as 6 P naught V naught, and other side we are going to get this as our 4 P naught V naught. So this is equal to our, this is our 6 P naught V naught minus 4 times P naught V naught is equal to twice P naught V naught. So this is our work done during BC. And we are left with only part D, the maximum temperature attained by the gas during the cycle. And for the maximum, one second, I forgot to solve one part left. I only calculated to work done, I have to find out internal, because final is our QBC. So we find out the change in internal energy, that we can say our delta UBC will be equal to N C of V and delta of T. Delta of T we can find out by TB, which will be equal to our 3 P naught V naught upon R, and we are having our TC, which is our twice P naught V naught upon R. Therefore we get delta of T is equal to TC minus TB. So we get this as our twice P naught V naught upon R minus thrice P naught V naught upon R, which will be equal to minus P naught V naught upon R. Now we can find out our QBC, which will be equal to our work done is our, this internal energy is P naught V naught upon R, and this comes as our plus we have to find out this. I only found out delta of T, so we substitute it, we get our this change internal energy equal to number of moles is 1, and this is our 3/2 times R minus P naught V naught upon R. R and R cancels out, so this comes as minus 3/2 P naught V naught. Now we can find out finally. So we get our QBC will be equal to internal energy is 3/2 P naught V naught, and work done is our plus twice P naught V naught. So this comes as 4 minus 3 will be equal to 1. So we get this as our P naught V naught upon 2. Now we come to the maximum temperature, that is part D. And from the, you can see our graph, we can make a observation that the highest temperature is along BC. Okay, so we can say highest temperature is along BC, and we can use our equation, that is P is equal to nRT, as well as the equation of our equation of the line BC. Okay, so we can say that our equation was our P is equal to minus 2 P naught V naught multiplied by V plus 5 times P naught. And from our ideal gas equation, that is equal to PV is equal to nRT, we can write that our number of moles is 1, so we can say our T is equal to PV upon R. We substitute our this equation of the pressure, so we get this temperature T will be equal to 1 by R, and we having this minus twice P naught V naught and multiply by V, so this comes as our V square plus 5 P naught times V, and we have to find out the maximum value, so we differentiate it. Okay. So we can say our dt dV is equal to, this comes as minus 1 upon R, and this will be minus V square will be 2V square, so this comes as 4 P naught V naught times V plus 5 times P naught, and equating equal to 0. Therefore, we obviously this R cannot be equal to 0, and pressure will not be also equal to 0. So we can just ignore these terms and we can write this as minus 4 upon V naught V plus 5 is equal to 0. This gives us minus 4 times V upon V naught is equal to minus of 5. 5 minus and minus goes away. So from here we get that our V naught will be equal to 5 upon 4 times V. Now we can find out our pressure and then we come to our maximum temperature. So you can say our pressure P will be equal to minus 2 P naught V naught. Substitute value of our, one second, we have to find out V, not V naught. So we can say our V is equal to, this comes as 5 by 4 times V naught, and we substitute value of our V in the equation. So this comes as a 5 by 4 times V naught and this comes as plus 5 times P naught. V naught and V naught cancels out and this goes by 2. So we are left with 5 by 2 P naught minus 5 by 2 P naught plus 5 P naught, and this gives us 5 by 2 times P naught. Now we can find out our maximum temperature. So we can say our T max will be equal to, we already know value of P and V, we substitute it, we come this as 5 by 4 times P naught, 5 by 4 is V naught, and this comes as 5 by 2 times P naught divided by R. So this gives us 25 P naught V naught divided by 8 times R. So this is our maximum temperature. Next question. It was asked in the year 1998 and it states that a solid body X of heat capacity C is kept in an atmosphere whose temperature is TA 300 Kelvin. At T is equal to 0, the temperature of X is T naught 400 Kelvin. It cools according to Newton's law of cooling. At time T1, its temperature is found to be 350 Kelvin. At this time T1, the body X is connected to a large body Y at atmospheric temperature TA through a conducting rod of length L, cross-sectional area A, and thermal conductivity K. The heat capacity of Y is so large that any variation in its temperature may be neglected. The cross-sectional area of A of the connecting rod is small as compared to the surface area of X. Find the temperature of X at time T is equal to 3 times T1. So we can just draw a rough approximate figure for that. So we are having a body X and its temperature is given to us as 300 Kelvin. And later on, this body X is connected to a bigger body through a conducting rod, and that bigger body is our Y, and its temperature is said to be as our TA, that is our atmospheric temperature. So this is our basically figure. And so first of all, it is having a temperature of So we are having that the body is having a temperature of T naught at T equal to 0 is over 400 Kelvin. Okay. And after time T1, its temperature becomes 350 Kelvin. Okay. So here we are going to use Newton's law of cooling and try to find out our, you can say, okay. So let's start with our from temperature time T is equal to 0 to time T is equal to T1. Okay. So you can say from T is equal to 0 to T is equal to T1. Okay. And we are going to use Newton's law of cooling. And so we are given that at T is equal to 0, temperature of X is our T naught, which is our 400 Kelvin, and at T is equal to T1, our temperature of X is suppose T1, which is our 350 Kelvin. Okay. Atmospheric we know is given to us as 300 Kelvin. So according to Newton's law of cooling, we can write that our minus derivative of we can say rate of decrease of the temperature will be equal to constant K, and this comes as T minus TA, and we can write this as our dt upon T minus TA will be equal to minus K times derivative of T, and we integrate with respect to our temperature as well as our time. So we can say our integration is from our 400 to 350 Kelvin. So this comes as our 400 350 dt, and this comes as TA. A is our atmospheric temperature, that is our 300, is equal to minus K, and this comes as 0 T1 times dt. Now this is so on the left side that will be natural log of the denominator. So we get this as a natural log of T minus 300. The limits are from 400 to 350, and on the right side it will be coming as K times T1. Therefore we can just substitute upper limit is our first is 350, so this will be coming a natural log of 50 minus natural log of 100 will be equal to minus K times T1. This can be written as natural log of 50 upon 100 is equal to minus K of T1, and this goes by 2, so we get this will be minus of natural log of 2 will be equal to minus of KT1, or we can say our KT1 is equal to natural log of 2. Let us call the equation number 1. Now this is our, you can say, temperature equation basically for our first phase. Now we have to find out what will be the temperature during this phase. Okay. So you can say temperature during this phase this is T minus TA is equal to T naught minus TA, and this is e raised power minus KT, and we all know all the values, so we can write this as T will be equal to, this comes as about 300 plus 400 minus 300 e raised power minus KT, which comes as our 300 plus 100 e raised power minus KT. Now we come from time T1 is equal to 3T1. So we come from T is equal to T1 to T is equal to 3T1. And here we have to remember, in the first case the cooling was only because of our radiation. In the second case the cooling will be also because of conduction, because it is connected, as well as because of the radiation. So we have to keep this in mind. So we can say we are going to have a radiation plus conduction. And at T is equal to T1, our body X, which is having a temperature of T1, which is 350 Kelvin, is connected to body Y, which is at atmospheric temperature, that is our 300 Kelvin. Okay. And conducting rod, its area, thermal conductivity, and the length is given to us. Okay. So like I said, the body X is going to cool through radiation as well as the conduction. So we can write from here that radiation which is basically our Newton's law, and this gives us minus the radiated heat, rate of radiated heat is equal to H T minus TA, and where this H is equal to K multiplied by capital C. Okay. Now we come to the conduction, that is a rod heat lost because of the connection to the rod, and it is also said that the Y body is sufficiently large, its temperature is not going to change. And secondly, we can say conduction, and for conduction we can say that our this heat loss is our Q2, that is dQ2 by dt will be equal to K area length, and we come this as T minus TA. Okay. we know that our dq by dt, general formula, dq by dt is equal to our C, rate of change of temperature. Okay. So therefore we can write that our total heat loss rate will be C, rate of change of temperature, is equal to, this comes as our, let me write on the lower side, so this comes as C, rate of change of temperature is equal to minus H plus Ka upon L, and this comes as our T minus Ta. Now we can just make some adjustment here and get the equation. So we get this as dt upon T minus Ta will be equal to minus H upon C plus Ka upon Cl times dt. Okay. And this H upon C is nothing but equal to our K. Mind it, this is a small k. Okay. So we can write this minus, and this is a K plus capital K A upon Cl multiplied by dt. Okay. So here we are going to take a constant equivalent to this. This is a K prime. That is our cooling constant basically. Therefore, we can say that our new cooling constant, let us suppose that is our K prime, will be equal to, sorry, it is small k. K prime will be equal to K plus capital K and Cl. Therefore, our equation becomes dt T minus Ta is equal to K prime and times dt, and it's minus sign. Now we simply integrate it. It goes from our 350 up till, let us suppose, temperature is about T2, and this comes as dt upon T minus 300 is equal to, this is our K prime and this is our T1 to 3T1 times dt. And its derivation is quite easy. It will be coming as natural log of T minus 300, substituting a lower and upper limit. I'm just going to put the result. So we get this as our natural log of T2 minus 300 divided by 50, and this is equal to our, this will be coming as 2, and this will be minus 2 K prime times T1, and we can just solve this now. This comes as our T2 minus 300 upon 50 will be equal to, this will be our exponential, and this will be our 50 e raised power minus 2 K prime T1, which gives us our T2 is equal to 300 plus, sorry, here there is no 50, and this will be our 300 plus 50 e raised to power minus 2 K prime T1. Okay, and we substitute our K prime. Let's calculate that value. So we can say our K prime, which is our K plus Ka upon Cl, and for time T1 we can just write is a K prime T1 is equal to K T1 plus Ka T1 upon Cl, and we know that our K T1 is natural log of 2. Therefore we get this as our K prime T1 is equal to natural log of 2 plus capital Ka Cl multiplied by T1. And if we multiply it throughout by 2, so we multiply by 2, and therefore we can write this as our in the form of exponential. We get this as exponential minus 2 K prime T1 is equal to exponential minus 2 natural log of 2 plus 2 Ka upon Cl, and this is T1. And we can solve our right side. This is our e raised power minus 2 K prime T1. We can write this as e raised power, it comes as 2 natural log of 2 multiplied by e raised power minus 2 Ka upon Cl times T1. And this exponential, this will be coming as our 1 by 4. So we can write this equal to 1 by 4, and we have this as e raised power minus 2 Ka upon Cl times T1, okay, and which was required to substitute here. So we get our T2 will be equal to 300 plus 50 multiplied by 1 by 4 e raised power minus 2 Ka times Cl, and this is our T1. And we can just keep it, or we can just cancel. This comes as 2 and this comes as 25. So we get this as T2 is equal to 300 plus 25 by 2 e raised power minus 2 Ka upon Cl times T1. So this is our temperature. Next question. It was asked in the year 1998, and it states that during the melting of slab of ice at 273 Kelvin at atmospheric pressure, you have to check which of these 4 options is the correct one. And we have to understand that the, you can say, the melting process of our ice, which we call as a ice water system. Okay. So first of all, it changes from solid to liquid, and there will be no change of temperature, and then there will be, you can say the change in volume, because water is denser than the ice, so we have to remember that thing. So first is positive work is done by ice water system on the atmosphere. Okay, here both A and B, it is by and this is on. Rest of the, you can say, wordings or the statements are same. Okay, it is work done by and work done on. So we can check both A and B. So we have options A and B. And we know that our work done standard formula W is equal to P times change in volume. Okay. And here this delta V is equal to final volume minus initial volume. So we are mainly interested in change in volume. Therefore we can say that density of ice, because we know that the density of water is greater than density of our ice. Okay. And therefore we can say that the volume of water will be less than the volume of the ice. So from here we can find out our delta V, or we can find out delta V sign. So delta V will be equal to our volume of water minus volume of our ice. And from here we can say that there will be, this will be basically negative, because volume of ice is greater than volume of our water. Okay. So if it is negative, therefore we can say there is a decrease in volume. Volume decreases. And if volume is decreases, we can draw a conclusion that our work done by the system on the surrounding. Work done by the system on the surrounding. And okay, we have to do it in the positive and negative, so we can just so we can use the basic equation, which gives that our work done by the system will be equal to atmospheric pressure we have, and this is our delta V, okay, which we found is negative. So we get this will be our less than 0, and work done, one second, sorry, no, this we are going to find out, that's my mistake. So we calculated work done by the system on the surrounding. Okay, it's not the conclusion, now we are going to find out work done on the system by the surrounding. So we are going to find out work done on the system by the surrounding. And obviously this by the system and on the system will be negative of each other. So we can say work done on the system will be equal to negative of work done by the system. So therefore this will be coming as greater than 0. So this will be our negative and this will be our positive. Okay. And we can check that option A is incorrect, option B is correct. Okay. And C and D are also with respect to internal energy. One it increases, and C and D says decreases. So this is option B is correct. And now we come to our option C and D. C and D, which is basically internal energy, and we can use our first law of thermodynamics, which gives us that our delta U is equal to Q minus work done by system. Okay. And here Q will be equal to our mass into latent heat of fusion, because during the melting process the system is going to absorb the heat, and that will be equivalent to our latent heat of fusion, and which is our greater than 0, or we can say positive. And by the system we just calculated that this will be our negative. So by the system will be our negative. Therefore, if we substitute it, we get that our delta of U is equal to, this comes as M times LF minus, and we can write the formula that is a PTM and our delta of V. Okay. And this is our already positive, and this term is our negative. So therefore we are going to get that our delta of U will be positive, because negative and negative is going to give us a positive. Okay. And so delta U is positive. I think that's all. Okay. So it is going to increase. Option C is correct and D is incorrect. Option C is correct. Next question. It states that V, Vrms and Vp respectively denote mean speed, root mean square speed, and the most probable speed of the molecules of an ideal gas at absolute temperature T. The mass of the molecule is m. Then we have to find out which of these options are correct. And this is based on our journal formula, and we can write the formula first of all. First is our most probable speed, that is our Vp. Vp is given as square root of 2 kt divided by m. Then we are having a mean speed, that is our V, which is our 8 kt divided by pi times m. And then we are having RMS, which is equal to 3 kt divided by m and its square root, where k is our Boltzmann constant, m is the mass, and t is the absolute temperature. Now we simply compare them and we can get the answer directly. So we know that our Vp is equal to 2 kt upon m square root, and our V is our 8 kt upon pi m and its square root. So we can just write this our okay, so we can write this as 8 by pi, and that will be coming as approximately 2.5 kt upon m. And Vrms we already know, so we can write that our Vp square will be equal to 2 kt upon m, and our V square will be equal to 2.5 kt upon m, and Vrms square will be equal to 3 kt upon m. And from here, if you make, because one thing is common among them is our this kt upon m, kt upon m, and kt upon m. Okay, and so from here we can say that our 2 is less than our 2.5 is less than our 3. Therefore we can say that our Vp is less than our V is less than our Vrms. So I think it should be other side, so option C is correct. There is something misprint in it, so option C is correct, is correct. And then we come to the option A. No molecules can we have a speed greater than square root of 2 Vrms. Okay, and square root of 2 Vrms. Okay, so we need to find out about Vrms. We already know Vrms. We have to find out square root of 2 Vrms. So Vrms is equal to our 3 kt upon m and its square root. Therefore we can say square root of 2 Vrms will be equal to, this comes as 6 kt upon m and its square root. And we know that these three equations are basically based on the fundamental concept that is called as a Maxwell-Boltzmann distribution, and it is non-zero for all the speeds v which is greater than 0. So from here we can say that Maxwell Boltzmann distribution is non-zero for all speeds v greater than 0. Okay. Therefore, we can say from here that there is a small probability that the molecules are going to have a speeds greater than any finite value, and that finite value will be also inclusive of square root of 2 VRMS. Okay. So we can say that because it says that no molecule, but according to this probability distribution law, it's possible that the speeds can be greater than this square root of 2 VRMS. So we can say that molecules can have speed greater than square root of 2 VRMS. Okay, this is only based on the probability. So option A is incorrect. And now we come to the option B. And option B is with respect to our Vp, and we can say our Vp is equal to 2 kT by m and its square root. So we get our Vp by square root of 2 is equal to kT by m. Okay. Once again, that okay, from here we can also say that let me write it here. You can also say that the probability density at V is equal to 0 is equal to 0. Okay. But it increases to a maximum value which is given by us maximum value at V of P. Okay. So it means the velocity of the molecule is going to lie between 0 and our Vp. Here it is Vp square root of 2. So we can say molecules have speed between 0 and Vp by square root of 2. And it says that no molecules can have less than this. So this option is also incorrect. Okay. So option B is incorrect. And we come to option D, that is our average kinetic energy. We have the basic formula, that is our average kinetic energy of molecule will be equal to our half m v square, which is basically our half m RMS square, and VRMS we substitute, we get this as kinetic energy average will be equal to 1 by 2 m, and this comes as our 3 kT by 2 times m, sorry 3 kT by m, not 2. Here this m and m cancel out, and this comes as over 3 by 2 times kT. Okay. And we have to find out in terms of Vp, so we can use our equation for Vp. We can say our Vp square is equal to 2 kT by m. So this gives us that our kT will be equal to Vp square m divided by 2. So we get kinetic energy average will be equal to 3 by 2 multiplied by m Vp square divided by 2, which comes as 3 by 4 m Vp square. So option D is correct. Correct. Next question. It was asked in the year 1999. It states that 2 moles of ideal monoatomic gas initially at pressure P1 and volume V1 undergo an adiabatic compression until its volume is V2. Then the gas is given heat Q at constant volume V2. So part A is our sketch the PV diagram, and okay, so let's draw the PV diagram. And this is our adiabatic compression. So this is our pressure P, and this is our volume, and initially is a P1 V1. So let us, and it's compression. So let us start from here. This is point A, P1 V1, and it is compressed. So it is, let us suppose, goes like something like this, and it reaches a B, and here let us suppose pressure is above P2 and volume is over V2, or we can just, so this becomes our V1 V2, this is our P1 and this is our P2. Okay. And then it states that it is given as heat at constant volume V2. Okay, okay, I should have drawn it. Let me redraw it, because of the heat at constant volume it is going to change. Volume, pressure, and we have A P1 V1, B P2 V2, V2 V1, and this is our P1 and P2. Okay, then at constant volume it gives in heat, so it is going to rise up till some point, and let us suppose this point is our C, and the pressure at this particular point is suppose P3. Okay, so this is our, so AB is our adiabatic and BC is our isobaric heating. Okay, so it goes like this. Part B, find the total work done by the gas, total change in internal energy, and the final temperature of the gas. Okay. So total work done, we have adiabatic compression, and then we have our isobaric heating. Okay. So let us start with our adiabatic compression. And adiabatic compression is from A to B, and for adiabatic we know that our this heat that is our Q will be equal to 0. So you can say from Q A to B will be equal to 0, and we have change in volume from V1 to V2. Okay, and 2 moles are given to us, so we have number of moles is equal to 2, and gas is given to us as monoatomic, therefore we can write our C of V will be equal to 3 by 2 times R, and ratio, adiabatic ratio, that is our gamma, will be equal to 5 by 3. So therefore we can say by first law of thermodynamics, our delta U is equal to Q minus W. Delta, this Q is 0, so we get this delta U is equal to minus of W. Okay. And we can write this as U of AB, and this is work done of AB. Now we can find out our this delta UB. Okay. So we get this as our delta UAB will be equal to N of CV, and this comes as T2 minus T1, and N is about 2, C of V is about 3 by 2 times R, T2 minus T1, 2 and 2 goes away, so we are left with this as 3 of R, T2 minus T1. Therefore we get that our work done A to B will be equal to minus of 3R T2 minus T1. Okay. And we have to find out the temperature also. Okay, so because then we can find out, okay, let's find out the temperature now. So we can use our ideal gas equation. Ideal gas equation, PV is equal to nRT. Okay. So for our this A, we can write that our T1 is equal to our P1 V1 upon nr, which comes as P1 V1 upon 2r. And we can write for B. For that we are going to use our adiabatic relationship. So we can say that for adiabatic process, we know that our P1 V1 raised power gamma is equal to P2 V2 raised power gamma. So from here we can say that our P2 is equal to P1, and we have this as V1 upon V2 whole raised power gamma, and gamma is 5/3, so this can be written as P1 V1 upon V2, and this is 5/3. Now we can find out our T2, and we can say that our T2 is equal to our P2 V2 upon 2 times R, and we substitute it, we get this as our V2 upon 2R multiplied by P1 V1 upon V2 5 raised power 3, and this is our V2 raised power 1, and here it will be coming as V2 raised power 5/3, so this will be coming as minus 2/3. So we can write this as our P1, and we have our V1 5/3, and we have our V2 minus 2/3, and this comes as divided by 2 of R. Okay. And we can write this in terms of T1, so we get our T2 will be equal to, because our V1 we can write as 1 plus 2/3. Okay, so you can write this as our P1 V1 multiplied by V1 2/3, and this is our V2 minus 2/3 and whole divided by 2/R. So this comes as our P1 V1 divided by 2R, and we have our V1 upon V2 whole raised power 2/3. So this comes to as our T1 V1, and this comes as 2/3. Next, now we can find out our delta U2, because we know that our T1 and T2. So we get our U AB will be equal to 3R, and this comes as our T1 V1 upon V2 2/3 minus T1. T1 we can take as common, so this comes as 3R T1 V1 upon V2 whole raised power 2/3 minus 1. And we can substitute T1 in terms of P1 V1 and R. So we get this as delta U of AB is equal to 3R times P1 V1 upon twice R, and here R and R cancels out, and this comes as our V1 upon V2 2/3 minus 1. Okay. So total work done, that is our WAB will be equal to minus of, because Q was 0, so this comes as 3/2 P1 V1, and we have this as V1 upon 2 whole raised power 2/3 minus 1. Okay. So this is our work done. And we have to find out the change in internal energy. Okay, final temperature also. I think temperature. Okay, let's find out the change in internal energy, which we found out, no? Yeah, we already found out. This is our change in internal energy. No, not this one. We can use this one. Any expression we can use. So this is our change in internal energy, work done, and then we have to the final temperature because heat is supplied, and it moves to C, and this is our isochoric process. We can say our B to C, which is our isochoric heating, okay. And because it is isochoric, therefore we can say that the work done for our BC will be equal to 0. Thus we can write that the heat supplied for our BC will be used entirely in the change in internal energy, and this we can write N of Cv, and this is our temperature is suppose our T3, and this is minus T2. Okay. So let me put here temperature T1, T2, and here temperature is T3. Okay. Volume is same, volume is not going to change. Number of moles are 2, so this comes as 3 by 2 times R, and we have this as T3 minus T2. 2 and 2 goes away, so we get our Q of BC will be equal to 3 times R, and this we have our T3 minus T2. So from here we can write that our T3 is equal to this comes as our T2 plus 1 by 3R times BC. T2 we already know, so we substitute it here. We get this as our P1 V1 upon twice R, and this comes as V1 upon V2 whole raised to power 2 by 3 plus 1 by 3R, and this comes as Q of our BC. And one second. Okay, heat supplied is Q, so therefore we can write QPC in terms of Q. So we get our T3 will be equal to P1 V1 upon 2R V1 upon V2 whole raised to power 2 by 3 plus Q upon 3R. So this is our final temperature. Okay. Anything else is missing? Work done, we have found out total work done. Okay. Oh yes, we have to find out everything is total. 1 second then. So we found out work done because of AB and work done because of BC was 0. So total work done is our this part only. Okay, so let me rewrite it. So we have our total work done. That is our W will be equal to W of AB plus W of BC, and W of BC is our 0, so this comes as minus 3 by 2 P1 V1, and we have this as V1 upon V2 whole raised to power 2 by 3 minus 1, and total change in internal energy and let us suppose that is our delta U. Delta U will be equal to delta of AB plus delta U of our BC, and for our BC is nothing but our heat supplied. Okay, so we can write that our delta of U will be equal to 3 by 2 P1 V1 V1 upon V2 whole raised to power 2 by 3 minus 1 and plus heat supplied, that is Q. So this is our change in internal energy and this is our total work done, and final temperature is T3, which we have already found out. So this is our final temperature, so this is not a problem. Okay, so this completes all the 7 questions. Thank you.